calorimetry. Here's an example of a calorimetry problem. And calorimetry is you use a calorimeter, which is a device that can be as simple as a coffee cup with water in it, or is something a little more complicated, such as a bomb calorimeter, where you can do combustion reactions that generate a lot of gas inside of it. But either way, the calorimeter is a device that measures temperature changes and has a heat capacity associated with it, where you can figure out how much heat is gained or lost from or to a chemical reaction. But anyway, to do calorimetry problems, it's useful to draw pictures. And your picture should always contain three things. 1, the calorimeter. 2, a reaction of some sort, or chemical, some process. And 3, a thermometer. So here, what's going on is 6 grams of calcium chloride is being dissolved in 3 milliliters of water, and that causes the temperature of the solution to increase 3.43 degrees Celsius. Assuming the specific heat of the solution is 4.18 joules per gram degree Celsius, the specific heat capacity of water, and assuming the calorimeter absorbs no significant amount of heat, determine the enthalpy for the reaction. So the reaction being calcium chloride, 1 mole of calcium chloride, solid, when it dissolves, we yield 1 mole of calcium cations and 2 moles of chloride anions. So to draw a picture, we have a coffee cup, I'm no artist, I'll admit it, but you don't have to be. So there's the coffee cup with a calorimeter in it. It has 300 milliliters of water in it. What's not included in the question but should have been is the density of water. It's 1 gram per milliliter. So 300 milliliters of water is 300 grams of water. And in the water, you had 6 grams of calcium chloride put in it. And it dissolved. And then the temperature rose or increased 3.43 degrees Celsius. So delta T is 3.43 degrees Celsius. So that's taking all that information and putting it into a picture. So we have a mass of water, we have a mass of a chemical, a reaction, and we have a change in temperature. So fundamentally, calorimetry problems can be understood initially using these two terms, where the minus sign is just there to indicate that whatever the value or the heat absorbed by the calorimeter, the reaction is going to be equal but opposite in sign. So that's the importance of the thermometer in your drawing. So if the increase in temperature was 3.43 degrees, the heat of the calorimeter is going to be positive. the temperature went up. It increased 3.43 degrees. That's an endothermic process from the perspective of the calorimeter. You determine that first, which means that the Q of the reaction, the calcium chloride dissolving in water, must be negative. It's going to be equal in magnitude, but opposite in sign. So by doing that first, we've got an idea of what the signs need to be. And there are two formulas for Q from the chapter, from chapter 5. Q is equal to MCAT, MC delta T. This is often used when you have a specific heat capacity that's known. It has a mass term. And then there's Q cat. This equation is often used for when you are for your calorimeter. Calorimeters oftentimes have a heat capacity that's for the whole instrument. But of these two, for this problem, we have a mass of water. We know its heat capacity is 4.18 grams or joules per gram degree Celsius. And we have a change in temperature. So mass, change in temperature, and up in the problem is the specific heat capacity. So Q, 300 grams of water. The question said we can assume that the solution is going to have the same heat capacity as water. So 4.18 joules per gram degree Celsius. And the change in temperature is 3.43 degrees. Celsius. And if I do that math, I get 4,301 joules. That's equal to Q of the calorimeter. The calorimeter holds the water and absorbs that much energy. Resized everything. So if Q of the calorimeter is 4,301 joules, that means Q of the reaction is negative that many joules, negative 4,301 joules. Equal magnitude, opposite in sign. Calorimeter was positive, the reaction's negative. But the question's asking the enthalpy for the reaction. The reaction is for 1 mole of calcium chloride yielding 1 mole of calcium cations, 2 moles of chloride anions. So this is per 6 grams of calcium chloride. But chemical equations are in molar amounts. So what has to be done is this has to be converted to moles. You've done that a lot by this point in the semester or in your chemistry careers. But if you've got 6.0 grams of calcium chloride, to convert it to moles, you have to divide by its molar mass. 1 mole of calcium chloride weighs 110.98 grams. equal to 0.0541 moles of calcium chloride. So to find the enthalpy of the reaction, you divide this number by the molar amount, and that the enthalpy, that will give you the enthalpy in the format it should be, which is per mole. Negative 79,000 joules, or 79.5 kilojoules. That's the process. More calorimetry practice. We'll start by drawing a picture. So here it's a little different, but calculate the number of moles required of methane required to heat 200 milliliters of water, enough to make a cup of coffee or tea, from 20 degrees Celsius to 100 degrees Celsius. So we're looking for a delta T of 80 degrees Celsius. It's positive, going from 20 to 100. And assume that only 50% of the heat generated by the combustion is used to heat the water. The rest of the heat is lost to the surroundings. So underneath this coffee cup, you've got methane combustion. So that's the reaction that's going on. So remember that your picture needs to have a thermometer, a calorimeter, and a reaction of some sort. So that's the flame underneath. We're told that enthalpy value is negative 890.4 kilojoules. However, we're told that this process is 50% efficient. So half of the heat generated goes to the water. The other half is going elsewhere. It's not going to the coffee cup or the tea cup. So the true enthalpy value, or the useful enthalpy value, I should say, is going to be half of this value. So that negative 445.2 kilojoules is what we need to use in this instance because it's 50% efficient. So I reframed everything. Q, the calorimeter, or the coffee cup, in this instance you're brewing coffee or tea. Since the temperature's going up, that's what that delta T is for, that thermometer. That's a positive value. And then Q of the reaction, it's given away, but that's negative, and that's given away in the enthalpy value. So we can use either Q is equal to MCAT or Q is equal to CAT, just depending on the process here, but we know that we're dealing with water, and we've got 200 milliliters of it. Call the density of water is 1 gram per milliliter, and that the specific heat capacity of water is 4.184. The previous problem is 4.18 joules per gram degrees Celsius. So Q is equal to MCAT. Q of the calorimeter is the mass of the water, which is 200 grams, times the specific heat capacity. Should have started that someplace else. And then the change in temperature is 80 degrees Celsius. Box that in. So if I do that math, the coffee cup needs to absorb 66,944 joules, or 66.944 kilojoules of energy. So that's how much it needs to absorb. So we have our reaction equation, we have our reaction enthalpy, and the question's wanting to know what is the number of moles of methane required to generate that much heat. Per 1 mole of methane, you get this many kilojoules of energy normally, but again, referring to earlier, we're only getting half of that, because half of the heat goes to the water, the other half is billowing out to the sides, like if you were normally boiling water. So we've got 66.944 kilojoules needed. You get 445.2 kilojoules per 1 mole of methane from our balanced chemical equation. Now the minus, since Q of the calorimeter is positive, it's absorbing heat, that means the reaction will have a negative sign, its opposite sign, or negative signs will cancel. And when in doubt, you can't have a negative mole. So you can't have a negative mass, so those signs would cancel out anyway. But if I do that math, you would need 0.150 moles of methane. That's how much methane gas you would have to burn at 50% efficiency to get a cup of coffee or tea going.